Imagine trying to defuse a live bomb, right?
Yeah.
But instead of any practical experience, you're just flipping through a 100-page paper manual.
Oh, yeah. It sounds completely absurd.
Right. But, I mean, until today,
Right.
that is essentially how we've been training workers for, some of the most dangerous high-stakes jobs on Earth.
It really is. You're given this massive binder or maybe a multiple choice test, and then you just have to somehow apply that flat, lifeless text to a complex physical reality.
Which is exactly why we were doing this deep dive today for you, the listener. Because, well, bridging that gap between knowing something in your head and actually doing it with your hands has been like the white whale of industrial training for decades.
It's a massive disconnect.
Yeah.
And that brings us to the focus of today's session, which is this incredibly dense press release from an innovation lab called EON AI Ventures.
And they're announcing Genesis 3.0, right? From
Hey.
April 21, 2026.
Exactly. And whether you're trying to stay ahead of the bleeding edge of AI or you're just fascinated by how humans acquire complex skills, I mean, this document outlines a total paradigm shift.
Because it's allowing the actual subject matter experts, the people out in the field doing the physical work, to build fully interactive physics-based simulations just by typing plain English.
Yeah, that is the core disruption we really need to establish right up front. Genesis 3.0 just totally bypasses the traditional gatekeepers of virtual reality.
Wow, so no developers needed.
None. You don't need software developers. You don't need 3D artists. There's absolutely no complex coding. And it runs entirely in a standard web browser. Zero installation required.
I really want to look at why that is so necessary because, the current state of enterprise training in industries like energy or aerospace, it just seems practically archaic.
Oh, it's brutal. The baseline problem is that building a single extended reality or XR training module right now is just agonizingly slow and wildly expensive.
The source points out some crazy numbers for that, right?
Yeah, an average module takes anywhere from 6 to 12 months to build, and it costs between $50,000 and $150,000.
Because you need an entire studio. You've got a 3D artist making the models, an instructional designer planning the lesson, and then a software developer trying to translate all of that into computer code.
Exactly.
It's basically like having a master chef who can't cook a meal unless they first learn how to, forge and weld their own pots and pans. The translation bottleneck just ruins the whole process.
And the tragic part is, after a year of development and $100,000, the end result usually lacks the two things you actually need to learn a physical skill.
Which are real-world consequences and muscle memory.
Right.
The press release actually includes this brutal quote from Dan Lecherskar, the CEO of EON AI Ventures. He says, the training industry has been building PowerPoint with a 3D viewport bolted on.
Ouch. But I mean, it hits hard because it's entirely accurate. You have petrochemical engineers managing highly volatile pipeline pressures.
Or cardiac nurses dealing with human lives.
Exactly. And their training simulation is just this generic, pre-rendered slideshow.
It's a slideshow because there are no actual physics running in those traditional modules, right? Like if a trainee turns a digital valve the wrong way, the pressure doesn't dynamically build up and blow a gasket.
No, not at all. The program just plays a stock animation of an explosion, regardless of what the user actually did.
Okay, let's unpack this. Because if we look at the broader tech landscape, we've had incredibly powerful video game engines for years. I mean, Unreal Engine, Unity, they simulate physics perfectly.
They really do.
So why are industrial simulations still so disconnected from reality if those tools exist?
Well, the limitation has never been the hardware or the game engines themselves, It's the authoring friction. If you want to build an interactive scenario in Unreal Engine, you have to use complex visual node graphs.
Which is essentially wiring together hundreds of intricate logic boxes to tell the computer what to do.
Right. And even with newer AI tools like Unity Muse, the system generates raw code that a human developer still has to review and debug. So the friction isn't rendering the 3D graphics. The friction is forcing a human expert to think like a computer.
So the solution is just removing that translation layer entirely. EON AI Ventures claims to have solved this with a system they call Describe and Wire.
Based on the source, this is an industry first. The subject matter expert doesn't code anything. They literally just type a sentence.
Okay, picture this. A veteran plant manager is sitting at a laptop. They look at a 3D model of a boiler and they just type.
When the trainee clicks the red valve, the pressure gauge drops to 0, the steam vent opens with a hiss, and the warning light turns green.
Wait, really? Just a regular sentence. I want to dig into the actual mechanism of what happens the moment they hit enter. Because it's obviously not just doing a simple text search.
No, it has to understand spatial relationships. Genesis 3.0 uses an AI parser that dissects that sentence in real time. First, it uses something called fuzzy mesh matching.
Let's define that, because fuzzy mesh matching sounds like a serious buzzword. What is it actually doing?
Rather than looking for a file specifically named, like redvalve.obj, the AI is looking at the mathematical structure of the 3D environment itself.
Oh, so it's looking at the geometry.
Exactly. It compares the geometric curves, the vertex clusters, and the spatial relationships to known patterns. It figures out which cylindrical mesh operates like a valve and which one happens to be red.
Wow. And then it maps the verbs from your sentence like drops or opens to actual physics actions.
Right, and it automatically pulls a hissing sound from a library of procedural audio. The system actually has 22 different audio sources for that.
And it triggers all those effect types simultaneously. The documentation lists 11 different effects. Rotation, translation, scale, color change, all happening at once based on that single sentence.
But the truly staggering technical achievement here is where this processing actually happens.
Because it's not in the cloud, right?
Exactly. The parser doesn't send your massive prompt to a server and wait for a coded response. It generates these structured event rules locally, right in your web browser, at sub-millisecond speeds.
Here's where it gets really interesting for you listening. For enterprise companies, data security is everything. You do not want to upload your proprietary nuclear reactor schematics to a public AI server.
Oh, definitely not. By doing it locally, the person who actually knows the equipment becomes the software developer instantly, without exposing any corporate secrets.
It fundamentally changes who gets to build training software. But, a labeled 3D model with a few interactive parts isn't a certified curriculum.
Right, throwing a bunch of clickable tools on a screen doesn't teach an apprentice how to use them safely.
So how does the platform organize that chaos into a real lesson plan?
They've engineered what they call the 5 layers, 5 minutes pipeline. It's a formalized assembly line designed to take a raw 3D file and produce a scored training experience in under 5 minutes.
Okay, let's break down the mechanics of that assembly line, starting right at minute 0, layer 1.
Layer 1 is the 3D world. You just drag and drop a standard GLB model into the browser.
And just to clarify for anyone unfamiliar, think of a GLB file as basically the PDF format for 3D objects. It's just a widely used standard that packages everything into one easy file.
Exactly. So once you drop that file in, the AI auto-scans every geometric mesh. It uses 23 distinct pattern rules to identify the anatomy of the machine.
Wow, and it does this fast.
Under 10 seconds. It can look at a 72-part industrial model and fully annotate which part is a motor, a switch, or a door, assigning confidence scores to every single component.
So the AI builds its own spatial map. It knows it's looking at a red valve.
Hmm.
But a labeled map doesn't inherently teach you a sequence. How does it learn the actual steps of the job?
That happens at the 30-second mark in Layer 2, which is the procedure. There are 2 options here. You can use an AI-ready mode where the system analyzes the parts and attempts to infer a logical sequence.
Or, and this is probably much more important for compliance, a trainer can use upload SOP mode, right?
Yes. Upload standard operating procedure. You upload your dry, text-heavy company manual, and the AI maps the specific steps from your document directly to the 3D components it just identified in Layer 1.
So it preserves your exact corporate terminology.
Yeah.
That covers the specific manual. But, I imagine some of these actions have to be highly repetitive across an entire industry.
Oh, for sure.
Like checking a safety valve or turning off a breaker is probably the same basic mechanical motion across a dozen different machines.
Which is why Layer 3, at the 1-minute mark, introduces the recipe layer. These are reusable template patterns.
Oh, nice.
Yeah, a safety lockout procedure in a factory is almost always some variation of inspect the area, toggle the power, and tag the machine. You save that recipe and share it across different models so trainers aren't constantly reinventing the wheel.
Work smarter, not harder.
Yeah.
Then we move into layer 4 at the 2-minute mark.
Layer 4 is the mission. This is where you start wiring the procedure steps to the 3D mesh using those describe and wire sentences we discussed.
You attach your physics effects, your hazard warnings, and sounds, turning the static steps into an interactive tracking system.
Exactly. And then right at the 5-minute mark, you reach Layer 5, the training layer. This is where the actual pedagogy kicks in. It's a 4-phase loop.
Let's hear the phases.
Show me where the AI demonstrates the task. Guide me, which provides coached practice where the visual hints slowly fade away, forcing the learner's brain to actually recall the steps.
Love that.
Then let me try, which is independent repetition. And finally, Evaluate me.
And that evaluation phase is a rigid, scored assessment. It factors in configurable weights, penalizes mistakes, adds time bonuses, and generates a professional PDF certificate with a unique verification URL upon passing.
It is essentially an automated cognitive funnel. You pour your company's dry manual into the top, and 5 minutes later, out pops a fully interactive, certified testing environment.
It's incredible. But an automated course completely falls apart if the simulation feels weightless. If a trainee drops a digital wrench and it just floats in midair, the illusion breaks. The brain stops treating it like a real-world hazard.
Physics dictate immersion. And the source makes a major point to emphasize that Genesis 3.0 does not use fake, pre-rendered animations. It integrates the Havok physics engine.
For context, Havok is the same incredibly robust physics engine used to power massive, chaotic video games like Halo and The Legend of Zelda.
Right, but the press release notes they've compiled Havok to WebAssembly, meaning they've taken this heavy desktop-grade software and translated the code so that standard browsers like Chrome or Safari can run it natively.
At a flawless 60 frames per second. That is wild.
And that allows for incredible granularity. The objects inside Genesis 3.0 have calculated mass ranging from half a kilo up to 10 kilograms. Gravity operates at precisely 9.81 meters per second squared.
So if you drop a digital part, it accelerates exactly as it would in reality. If you grab a heavy motor, the digital interaction actually resists your input based on that actual weight.
Objects even bounce off the floor with physically accurate restitution.
And that physics engine is tied directly into assembly and disassembly using a constraint graph. This is fascinating to me because it forces consequence.
A constraint graph essentially maps out hierarchical logic dependencies and invisible boundaries. It means you physically cannot pull a fuse out of a machine before unlatching its protective cover.
The geometry simply will not clip through itself.
Exactly. If you try to force the wrong sequence, the simulation produces a red glow and logs an error. If you get it right, snap zones show green highlights and ghost outlines to guide placement. It is real-time resistance responding to your actions.
But, it's one thing to make a physics engine work perfectly in a highly controlled demo lab. Enterprise companies have thousands of workers. If this requires everyone to buy a $3,000 gaming computer in a wired VR rig, it's a non-starter.
Accessibility is the make-or-break factor here. Genesis 3.0 operates off a single code base, accessed via a single URL. It runs natively on high-end stuff like a MetaQuest 3 or Microsoft HoloLens 2, sure.
But it also scales down, right?
Yes, it runs on iPads utilizing LiDAR, which uses lasers to measure depth and map the room, as well as standard Android devices and desktop browsers. Zero install.
The hardware solution they came up with for mobile devices is brilliant. The source highlights an invention from the founder, Dan Lidgerskar, called the chopstick controller.
It's so clever, it essentially turns any smartphone's built-in gyroscope into a virtual 3D laser pointer.
It's similar to how a Nintendo Wii controller works, but mapped over a real-world industrial environment. You physically aim your phone and tap the touchscreen to grab and manipulate items.
It's an elegant bridge, though it does raise an inherent tension,
Yeah.
By scaling this down to run on a standard smartphone, they are consciously accepting a drop in visual fidelity compared to a dedicated VR headset.
But it's a pragmatic trade-off. They are bypassing the headset barrier. An imperfect simulation in the hands of 10,000 fieldworkers is infinitely more valuable than a photorealistic simulation locked in a lab that nobody ever uses.
Exactly. And to ensure trainees aren't just left reading floating text on those smaller screens, the platform includes a dynamic AI avatar guide system. It's built in 3 tiers to accommodate different hardware capabilities.
Break those tiers down for us. How do they differ?
So the first tier is the Mixamo avatar. It's a full-body skeletal human guide. It physically demonstrates the steps, walking over to the equipment at 1.5 meters per second.
And it uses quaternion interpolation, right, which is just the mathematical logic that allows the avatar to naturally and smoothly rotate to face a relevant part, rather than snapping to a grid like a rigid robot.
Right. Now, if you need more realism than that, you step up to the Heijan avatar. This tier provides photorealistic lip-sync speech for highly sensitive scenarios where human nuance really matters.
But what if you were on an older mobile device with limited processing power?
Then the system falls back to the third tier, the drone guide. It's a small floating drone that uses laser pointers and text-to-speech, ensuring you always have guidance regardless of your hardware.
And while that guide is helping you learn, the system is ruthlessly grading you. The gamification mechanics aren't just about collecting gold stars or badges. They tie into actual safety protocols.
Organizations can flag critical steps that trigger an immediate autofail if executed incorrectly, which is paramount for something like an electrical plant lockout procedure.
Right. If you skip cutting the power, the system doesn't give you a lower grade, it fails you, simulating a catastrophic real-world outcome.
Beyond that, the engine tracks daily streaks, utilizes competitive leaderboards, and even features an oral assessment module.
Oh, using speech recognition. So a trainee can literally explain the procedure to the simulation out loud to prove they understand the why behind the what.
Exactly. So we have local AI parsing, Havoc physics running natively in a browser, and dynamic avatars all working seamlessly together.
But looking at the launch metrics in the source material, this isn't just an experimental beta, is it?
The scale is massive. They are launching across 17 different industry segments: energy, smart manufacturing, healthcare, data centers, with over 1,100 courses built on 636 production-quality 3D models ready on day one.
And the press release includes a technical detail about their engineering architecture that I found really illuminating. They integrated 3 different massive AI models, GPT-4o, Claude AI, and Google Gemini, using a complex React 18 and PostgreSQL stack,
And they executed 13 features with 13 clean commits.
meaning zero code errors. That is like trying to build a skyscraper using blueprints from 3 different architects and having every single steel beam line up down to the millimeter.
It just proves that this is a highly mature, production-ready architecture. The system isn't buckling under its own weight.
Which naturally leads to the question of where this goes next. If the foundation is this stable today, what does the platform look like tomorrow?
The source outlines a very clear progression. Typing a sentence with describe and wire is just the baseline. The next step is voice integration. A subject matter expert will simply speak aloud to the AI, and the system will auto-confirm the physics rules.
Wow. From there, it evolves into conversational refinement, right?
Yeah, you could look at the simulation you just built and tell the AI, hey, make the consequences of step 2 more severe, and the AI will adjust the physics accordingly.
But the end game they describe is something they call zero authoring.
Zero authoring is the ultimate ambition. Eventually, the AI will simply understand the intrinsic rules of the physical world. A trainer won't have to explain that pushing a red button activates a burner or that opening a valve releases pressure.
The AI will just know how mechanical reality operates.
And they plan to connect this underlying knowledge directly to what they call field IQ, where these classroom procedures deploy straight into augmented reality smart glasses out on the actual job site.
We started this deep dive by talking about the absurdity of trying to learn a physical high-stakes job by reading a flat, lifeless manual. What EON AI Ventures has built isn't just an upgrade to a multiple-choice test. It's a completely new medium.
It entirely removes the friction between a master knowing a skill and an apprentice learning it. It injects the actual laws of physics, consequence, and spatial awareness into digital training.
And that leaves you with a deeply provocative thought to ponder. If an artificial intelligence engine is successfully internalizing the actual physics, the actual weight, and the actual consequences of our reality to the point of zero authoring,
Yeah.
well, how long until these training simulations become entirely indistinguishable from the real world? And when that moment arrives, when a virtual mistake carries the exact same psychological and physical feedback as reality, how will we define the difference between a simulation and actual experience?
That is the defining question for the next era of industrial training.
Thank you so much for joining us on this deep dive. Keep questioning, keep learning, and we will see you next time.